To start the review of linear circuit analysis, I will go over skip over the section on fundamentals. I think it's very basic and that's very easy reading, and start the review in the second section by discussing various elements, circuit elements. You'll find that the circuit element resistance is the fairly common one. We're all very familiar with resistance, governed by Ohm's law. V is equal to R times I. I is the current through the resistance, R is the resistance, and V would be the voltage across the terminals. All right? I'd like to go on to talk about voltage sources. There are two kinds of voltage sources. We have the voltage source that's much like a battery. It's independent. It's an independent, we're assuming idealism. It's an independent voltage source, and this is shown usually schematically in this fashion: circle, plus, minus, with terminals. In contrast to an independent voltage source, we have a dependent voltage source, and the dependent voltage source would have symbolically a diamond-shaped box like this, and it has a plus and a minus, and there's a voltage across here. But this voltage depends upon something else. It may depend upon a voltage in some other part of the circuit, or a current someplace else, or a temperature, or some other parameter. So this is now a dependent voltage source characterized by the diamond-shaped box. Now we also have two types of current sources. And as you can imagine, they're going to follow the same pattern as the voltage sources. The two current sources are, first of all, the ideal current generator, which we show as a circle with an arrow showing the direction of current flow. And this is a independent current source. But then sometimes we have to be concerned about the ones that depend upon something else. And here's a diamond-shaped box once again with the terminals. But now we have the arrow in here. That is now a dependent current source, where the current from this device depends upon some other parameter. Okay, so much now for two voltage sources, two current sources. Let's get back to resistance for just a moment. The resistance of a piece of wire depends upon a parameter, rho, which is its resistivity. And the resistivity is a function of temperature. Everything is referred to, when they talk about resistivity without implying a temperature, the implicit definition is that it's being referred to at a temperature of 20 degrees Celsius, or simply 20 degrees C. So I would write that rho 20, which is the resistivity at 20 degrees C, is a certain number. For instance, it's equal to 1.8 times 10 to the minus 8 for copper. Now, what are the units? I left some space for the units. The units of resistivity would be ohm hyphen meter, ohm meter, ohms times meters. So the resistivity would be 1.8 times 10 to the minus 8. On the other hand, if you take some material like nichrome, for instance, you find the resistivity there is 1.08 times 10 to the minus 6 ohms meter. This is for nichrome. And you can see quite an interesting contrast by 2 orders of magnitude, that the resistance is much, much higher for nichrome than it is for copper. Copper is notorious for a very low resistance. That's why it's used so frequently in conductors. Now, let's talk a little bit about this resistivity. The resistivity obviously is a function of temperature, depends upon temperature. And the dependence goes something like this. There's a coefficient called alpha, An alpha at 20 would be the temperature coefficient of the material at 20 degrees C. That'll be our standard basic definition.